Okay. Good day, everyone. I'm Renee Yager, the Director of Marketing at EPC, and welcome to today's webinar, Using Test-to-Fail Methodology to Accurately Predict the Lifetime of GaN FETs and ICs in Motor Drive Applications. This is the final installment of our summer series, which focused on GaN reliability in real-world applications. If you missed the first three installments where we discussed reliability in solar, DC-DC, and space applications, those replays are available on the website at epc-co.com. So before we get started, I would like to go over a few housekeeping items. You have the opportunity to submit text questions to the panel by typing your questions into the Q&A feature, which is at the bottom of your screen. You can send those questions in at any time. We'll collect those and address them during the Q&A session at the end of today's presentation. If you are participating in the rewards program, be sure to identify yourself to earn points for asking questions. If the question is asked as anonymous attendee, we won't know who to credit that question to. So now, without any further ado, I would like to introduce our speaker today. Dr. Shankay Zhang is Vice President of Product Reliability at EPC, where he leads the conduction of failure analysis for all GaN transistors and ICs. Prior to joining EPC, he worked as Senior Failure Analysis Engineer on RF MEMS devices in the mobile industry. He earned his PhD degree in Material Science and Engineering from Arizona State University, investigating low-loss dielectrics for cellular and advanced computing applications. He is the author and co-author of more than 20 technical papers. He is also a committee member and internal liaison for JEDEC's JC70 Wide Bandgap Power Electronic Conversion Semiconductor Committee. Shanky, thanks for joining us today.
Okay, thank you. Good morning, everyone. Today, we will be discussing using test-to-fail methodology to accurately predict projected lifetime of GaN devices in motor drive application. So why test-to-fail? Standard qualification typically produce 0 failures out of a relatively large group of parts tested. Therefore, it's quite challenging to apply the test result to a specific application that has a unique mission profile. That's why we need to test to fail and follow with failure analysis to understand the underlying failure mechanisms. Here is a list of stressors and the corresponding intrinsic wear mechanisms. The detailed methodology and the result were documented in this peer review book, GaN Power Devices and Applications. First, what's the benefits of GaN in motor? So here is a result showing the phase current when comparing silicon inverter with 500 nanosecond that time at 20 kilohertz PWM frequency versus GaN inverter using 14 nanosecond that time at 20 kilohertz in frequency, PWM frequency, where we can see that by eliminating that time, it leads to less distortion in phase current, less vibration, and less acoustic noise. And the second benefit of GaN motor is that by increasing PWM frequency, it can significantly reduce both input current ripple and input voltage ripple. And as a result, it can smoother out the phase current, as you can see the result right here. So here is another this table documents the benefits, another benefits of GaN motor, where we can see that by comparing silicon inverter and the GaN inverter, so we can eliminate the input inductor and the electrolytic capacitor by using GaN. So second point we want to highlight here is that although the inverter efficiency does not change much, but total efficiency is by using GaN is increased by a factor of 6.5%. So for motor drive applications, we identify 5 main stressors, which are gate bias and drain bias, because they're using an inverter 3 half-bridge topology, and then temperature cycling, and then next is a short circuit fault condition, and lastly is mechanical stress that is induced by the motor movement. So all 5 stressors are critical and affect the overall lifetime. So next, we will examine every single stressor, and then to look at the lifetime model and how they impact the motor drive reliability. So first, gate bias. To start off, let's look at our gate structure in this TEM cross-section image, where we can see the source metal, source field plate, and the gate. You may notice that there is a dark layer between the source metal field plate and the gate. It's actually a silicon nitride dielectric layer. Please keep this cross-section in mind because we will come back to this cross-section when discussing gate wear-out mechanism. So we conducted accelerated gate reliability testing, where we took our devices well beyond the datasheet limit and monitor how they fail. Here is the Weibull distribution plot, where the vertical axis is the failure rate and the horizontal axis is the time of failure in unit of seconds. We took 4 groups of devices, 32 parts each, and tested them at 8 volt, 8.5 volt, 9 volt, and 9.5 volt. As you can see in the Weibull plot, devices fail very quickly at 9.5 volt, but it took hundreds of hours to generate just 2 failures at 8 volt. After failures were identified, we conducted failure analysis. Here is the FA result at the failure site. So where we can see the cross-section of the failure site, the failure is happened between the gate corner and the metal one field plate. In fact, we analyzed a whole bunch of devices. All devices actually failed in a similar manner, sometime on the left side of the gate corner, sometime on the right side of the gate corner. Based on the FA result, so we were able to develop a good understanding of the underlying failure mechanism. So here it shows that what we understood about this failure mechanism. So we can explain this gate corner dielectric breakdown failure mechanism by using the 3 steps impact ionization process. In the first step, the electrons are injected into the p-GaN gate from the two-dimensional electron gas layer over the L-GaN front barrier. In the second step, electrons are accelerated by under the influence of electrical field. So where some electrons gaining sufficient kinetic energy to cause impact ionization and cause holes. In the final step, holes are trying to move away from the gate corner and become trapped in the silicon nitride dielectric layer, leading to a growing positive charge density as in QH, as seen right here. Once the charge density reached the critical density, so the dielectric ruptures, causing the catastrophic damage at the gate corner as observed in the previous FA result. So by understanding this 3-step impact ionization process, we developed this mean time to fail lifetime equation. Now let's see how well we can this mathematical lifetime model explain our experimental data. Here shows the impact ionization model is plotted against the measured data point of EPC 2212, where a good fit is found. If we keep the gate bias at and below 6 volt VDS max, we project less than 1 ppm failure rate for over 25 years of continuous DC gate bias. So next we will look at drain bias. To start off, we will look at the cross-section again. In this TEM cross-section image, we can see drain, field plate, gate, and source. So when devices are subject to high drain bias, we observed actually a lot of hotspot using AMI, a common failure analysis technique. Hotspot suggests that the electrons are getting accelerated by the high electric field and become hot carriers. Now, if we zoom in the hotspot image and overlay the hotspot image with the mask layout, Now we can find the hotspot predominantly occur at the edge of the drain contact, indicating that is where high electrons are trapped and therefore responsible for the dynamic radiation shift. Based on all the findings discussed, we developed a physics model to explain this hot carrier trapping mechanism. The electrons are accelerated by high electric field and then scattered by the lattice, become trapped in the passivation film by the drain contact, as showing that right here, where we highlight as the critical area, critical region. Now we align the band structure near the drain contact, where we can see a barrier, energy barrier that exists for the electrons to overcome. So the majority of electrons do not have sufficient kinetic energy to overcome the barrier. Only a small fraction of electrons do, and then subsequently get trapped within the silicon nitride dielectric layer. As more and more electrons are getting trapped, the barrier height is further enhanced by the trapped charges. So as you can see there right here. So this further barrier height or dynamic barrier height increase is the key for the lifetime model development. So today we are just showing that right here. This is the final expression that models to detail this dynamic trapping mechanism. Here shows a comparison of measurement and model for EPC 2045 and 100-volt GaN devices, operated at 4 different voltages and 3 different temperatures. We can see that good agreements between measurements and the model were found, which demonstrate the validity of the model. So now let's apply the drain lifetime model to motor drive. So in motor drive, basically, the GaN transistors are used in the 3 hot bridges. So 100 volts, EPC's 100-volt rated GaN solution is actually a good fit for this motor drive application. So let's see how well we do. Here is the resistive load hard switching test system we developed to model this hard switching turn-off characteristic, where we can also monitor the evolution of dynamic radiation in situ during the 15% duty cycle of on state in here. On the right shows the drain voltage turn off waveform with a bus voltage of 80 volt. So 80 volt bus voltage is considered the max recommended operating voltage in motor drive application. Here shows the test results. So we tested one representative EPC 2218, 100 volt GaN devices, and another EPC 2302, a PQFN packaged 100 volt GaN devices. So we found that less than 10% of radiation drift over 25 years of continuous operation at 80 volt and 100 kilohertz. So the linear line fit is based on the lifetime model we developed, showing previously. So this shows the good robustness of our 100 volt GaN devices under 80 volt bus voltage hard switching conditions. So, and also over voltage ring could also be happening in motor drive more frequently than we would like to during braking or some other operating conditions. Therefore, we developed this unclamped inductive switching test circuit as shown in the schematics. So where we can also monitor the evolution of RDSO in situ. On the right is the resulting 120 volt over voltage result that is produced by this unclamped inductive switching test circuit. So just this circuit is for a 100 volt device. When we overvoltage to 120 volt, this is just to simulate its abnormal over voltage condition in motor drive application. Okay, so here is the test result. So we tested 3 representative EPC 2218 100 volt rated GaN FETs from 3 different representative lots and wafers to 1.5 billion switching cycles at 120 volt over voltage spike, which is 120% of the 100 volts max rate voltage, where very minimum radius shift was observed. When we project the shift to 25 years of lifetime using the model we developed, resulting from the hot carrier injection, we observed that all data points fall on the projected line and project shift is less than 10%. So as a number of trapped electrons approach the number of electrons in the original two-dimensional electron gas, so we can now use the simplified model. So that's here's the result showing that we go to extreme at 150 volt, which is 150% of the 100 volt max rated voltage. Here it shows how well the device hold up under extreme over voltage conditions. Here we are taking our 100 volt generation 5 devices up to 150 volt. On the left are measurement at 75C. On the right are 2 different temperatures at 75C and 125C. Once again, the trapping of the carriers is reduced at higher temperature due to the reduction of mean free path of hot electrons. In all cases, the extreme over voltage conditions only leads to accelerated device wear out rather than catastrophic failures. So next, we will be discussing temperature cycling, the TC. So board level temperature cycling testing of EPC 2218 was done at 2 different conditions, which are minus 40C to 125C and minus 40C to 105 Celsius. At TC temperature at TC1 condition, minus 40 to 125. So we tested 2 groups of parts with and without underfill material. We generated another viable plot for 3 sets of temperature cycling test conditions. So most importantly, underfill material drastically improved the temperature cycling reliability, as we have yet identified any failures to date at 3,000 cycles. So by test to fail, now we are able to develop a general temperature lifetime model as shown right here, which is called Norris Landsberg model. N is the number of cycles to failure. A is the coefficient. The first term is a frequency term, which includes how many cycles that happens per day. The next term is a delta T term, which is the classic Kauffman-Manson equation. This term focuses on the solder fatigue wear-out mechanism. Lastly, is a Raynaud's term, which primarily to model the creep wear-out mechanism because solder joint fails faster at the hot temperature extremes. So that's why we put this Raynaud's term in our lifetime model. So here are the parameters for the lifetime model of EPC 2218. Now let's look at how do we use this temperature cycling lifetime equation. In other words, how can we apply the TC lifetime model to real world applications? So here is the result. So start with this the Norris Landsberg lifetime equation. Assume we have the Tmax at 125C, which is potentially a worst case scenario for a lot of applications. Therefore, the Raynaud's term become a constant on the right. Now let's plot a number of cycles to failure N as a function of delta T at 1% failure rate, where the result is showing on the right. And then let's look at another case where the Tmax is 100 Celsius. So now we plot the N, the number of cycles to failure, as a function of delta T at 1% failure rate based on the previous Weibull distribution. Now we can get the lifetime equation or a plot as shown on the red curve, highlighted here. So now we repeat the same exercise for Tmax 75C and 50C, where slight improvement in temperature cycling lifetime is observed as expected. So here just shows a methodology that can simulate temperature cycling condition where the ambient temperature is changing in a relatively slow ramp rate, and how we can apply the delta T and T max in that potentially the most critical parameters in real world application. So then to correlate the number of cycle to failure. And also EPC is in the process developing a rapid temperature cycling model that better emulate the motor drive temperature cycling scenarios during operation. Just stay tuned. The next we are going to discuss is short circuit. So short circuit is another motor drive specific fault condition that could be happening during operation. So we also, let's take a look what we have learned, the short circuit capability in GaN devices. Here we use fault under load method to conduct short circuit testing where the drain voltage is applied while gate is on. So we took a cohort of 8 EPC 2051 devices, also 100-volt rated GaN transistors. We took them to fail under 60-volt drain bias and the 6-volt and 5-volt gate bias respectively, and monitor and the time of failure, and which is report documented in this table. As highlighted right here, the mean time to fail under the 60-volt drain bias, 6-volt gate bias is approximately about 9 microseconds. If we use 60-volt drain bias and 5-volt gate bias under this short circuit condition, the mean time to fail is about 22 microseconds. So this table shows excellent short circuit capability of GaN devices. By the way, the typical normal gate operating condition is, we recommend it is 5-volt. So we also went to extreme. So we also tested the EPC 2051 device to 500 million short circuit pulses with a pulse width of 5 microseconds and 85 amp pulse current. 85 amp pulse current is more than double the pulse current rating, which is 37 amp. After 500,000 pulses, 500,000 pulses, we found that all electrical parameters are still within the detection limit. This also demonstrates the extreme robustness of GaN devices under short circuit testing conditions. Okay, lastly, today we will be discussing mechanical stress induced by motor movement. Because the inverter boards is usually located in close proximity of the motor, the surface mount gate GaN devices can experience certain level of mechanical stress induced by the motor movement. So let's take a look. We will look at one of the mechanical stress, which is bending test. So we followed IEC 60068 bending test standard for this bending test experiment. So as you can see, this image shows the methodology we adopted, which is a 3-point bending test following the IEC standard. On the right shows the EPC 2302 PQFM 100-volt rated GaN transistor surface mounted on the test board, because in this test we would like to conduct in situ resistance monitoring. So we actually develop a special daisy chain die that is assembled in this identical PQFM, the production PQFM package for this experiment. So we took a cohort of 10 devices, and then we test them all the way to 2 millimeter, which is the maximum bending specified by the IEC standard. So there's no observable resistance shift was found from time zero to 2 millimeter max bending, as you can see that right here. So we also per IEC specs, we are also required to conduct physical cross section to verify or quantify the amount of solder joint cracking. So here shows the physical cross section and SEM inspection result after the bending test, where there's no solder joint cracking observed. So we, per the IEC standard, we perform this kind of cross section on 3 random pick devices. All devices showed identical result, no solder joint cracking. Here just shows one representative device, physical cross section result. That also shows our PQFN package device also has a pretty good mechanical, can withstand pretty drastic mechanical stress induced by the motor, motor movement. So conclusion. So gates have very near zero failure rate when the gate bias is kept at or below the max rated voltage, which is 6 volt. GaN devices are projected to have less than 10% shift over 25 years of continuous operation at 80 volt bus voltage, 100 kilohertz frequency. Underfield chip scale packaged GaN devices showed excellent temperature cycling capability. A methodology is given to estimate temperature cycling lifetime in a real-world application for a variety of device sizes. GaN FETs demonstrate extreme robustness under short circuit testing. Lastly, PQFN packaged GaN devices also show good mechanical robustness when subjected to bore bending stress. Thank you.
All right, thank you, Shankar. So now we are going to begin answering the questions submitted during today's presentation. Also on the panel is Andrea Gorgerino, who's our Director of Field Applications Engineering. And as a reminder, you can still submit questions by typing them into the Q&A feature at the bottom of the screen. So our first question is regarding slide 20. What was the load current or load resistance?
20. So in this case, I believe the current is about the RMS current is about 5 amp. That's the low current during this test.
On slide 19, how was the thermal performance in this resistive testing?
So we use thermal camera. So the actual junction temperature we monitor is about 70, 75 Celsius approximately.
On slide 15, what do the error bars mean in the curve, especially for 25 years?
15.
Must not be 15.
I think probably they're talking about this one, right? So is this one? I guess.
I guess. Does it go out to 25 years?
So okay, yeah, so 25 years. So what we have done, so this is a good question. So this is a relatively 2 hours experiment. So we have actually brought a lot of devices, I think roughly approximately 8 to 1,000 hours of testing. They still follow this trajectory. And the error bar for this fit is plus and minus about 5 to 10%. Okay. So because if you test what we have learned during 1,000-hour testing, slight ambient temperature variation, because it's kind of hard to control over 1,000 hours in a lab space. So a small variation, because the log scale can change the projection quite a bit, but they're going to be averaged out over 1,000 hours of testing. So it's about plus and minus 5 to 10%.
In the context of GaN-based motor drive applications, how can the test-to-fail methodology be adapted to account for the combined effects of mechanical vibrations, thermal cycling, and voltage current fluctuations, which collectively contribute to failure mechanisms that may not be accurately assessed in isolated stress conditions?
So what we have done previously, and what we are going to do too, is that so each stress we can, if we can have a mean time to fail. So what we have done is that the overall lifetime is, say you have on the left side is 1 over, is going to be the least mean time to fail of each stressor that's going to dominate is essentially 1 over overall lifetime on the left side of the equation, and it is the summation of individual lifetime in 1 over mean time to fail. That's kind of summarize how individual stressors affect the overall lifetime. So that's the methodology we have adopted, and with a lot of literature support that. The way we develop that equation is based on fit rate. So based on JEDEC standard and a lot of literature, the total fit rate is equal to the sum of individual fit rate resulting from each failure mechanism. So we just so left is the total fit rate, the right is the simple summation. The fit rate is inversely proportional to the mean time to fail. That's how we put everything together.
Given the evolving nature of motor drive technologies and their integration into various industries, how can the test-to-fail methodology be made adaptable to different application scenarios? And what considerations are crucial for maintaining the relevance of failure prediction models as technology and operating conditions change over time?
So that's a good question, also a bit broad. I think I'm going to try to answer this question from 2 perspectives. One is that so I think just let's work together. Give us your specific mission, drain bias, gate bias, frequency, the current, thermal. So we can work together to give you a more specific, tailor-oriented, more specific lifetime projection. We can tell you which one we need to pay more attention, which one has a higher risk than the others. And then I think the second part of the question is the evolution, right? I think so the way we typically address is to use the worst case scenario. Say, for example, your typical bus voltage, for argument's sake, 48 volt, but we're considering the corner condition. The worst condition, like say the rain is can be like 60 or 80 volt. The way we're conducting this kind of estimation or projection is based on worst case scenario. We can estimate the corner condition. So the test condition can evolve, but it's still covered by the worst case scenario.
Okay. Considering the complex electrothermal behavior of GaN devices during motor drive operations, how can advanced thermal management techniques and predictive thermal modeling enhance the accuracy of lifetime projections by accounting for localized hotspots and transient thermal effects?
That is, Andrea, what do you think? I think this is more thermal. I can add.
Well, I mean, if you think of hotspots, I'm not sure it's very important. I would consider more a second order effect. If you look at our devices, they're very small. And so in the context of a motor drive, especially when you have a large heat sink, I expect that that's going to be a secondary effect. But in the terms of the system level, of course, yes, advanced thermal simulation tools like FEA tools are very important when you use GaN devices, because again, they're small devices, the power densities can be very high, and also the current density can be quite high. And so having a good understanding of the thermal environment especially close to the device, is very important in your design.
Will we have access to lifetime model parameters while designing converters with EPC GaN?
Well, the generic model and parameters has been published in a lot of, I think our phase reliability report is the best place to start. So if you're looking for very specific parameters or conditions, just let us know. We can help you.
Can you talk about controlling slew rates to protect motors from high DVDT? That might be an Andrea question too.
Yeah, I mean, I think that's always a good question. I mean, there's no difference versus every other motor drive design you have done. You know, at the end, GaN devices are very controllable with a simple gate resistor. So yes, you can slow them down. Of course, you don't want to slow them down too much. You know, our motor drives, I think, are in the range of 10 to 20 volts per nanoseconds today. That's our inverters designs, which is not that excessive for low voltage drives, I would say. Especially, of course, if you think of high voltage drives, you typically goes lower. But in the typical motor drives that we are addressing, in the 48 volts, let's say, I think those volts per microsecond are in the ballpark of what you expect. And if you have a particular need to go slower, like, you know, higher laminations, you can always slow it down a little bit. There will be a trade-off in switching losses naturally.
What is the effect of temperature on efficiency of motor drives as compared to silicon devices?
I would say it's very similar. I mean, the main contributors are, of course, in losses. When you think about losses, they are, if you think of inverter losses, not system level losses, inverter losses are basically conduction losses and switching losses. Conduction losses, it's RDS on. Both silicon and GaN have a positive temperature coefficient. Maybe, I don't know, maybe doubles from 25 to 150, maybe a little bit less. Typically, GaN has a little bit less temperature coefficient than silicon. And especially in our latest generation, that coefficient has been going down. It has to do with the ratio of, you know, the metal contribution versus the channel. So it will be less. The conduction losses will increase less with GaN. How much less you'll have to take a look exactly which generation device you're using and which device you're using. Maybe to give you an order of magnitude, maybe 20% less increase probably is a good ballpark number. Again, it could be 10, could be 30 in the latest generation, maybe even a little bit more. Switching losses, probably similar. You know, all the capacitors are fairly constant over temperature. The threshold is the biggest contributor there. The threshold, again, is very stable over temperature, so you have a better behavior. The threshold of silicon is actually going down with temperature significantly, but you know how that affects losses is I think you have to go into detail. But I would say switching losses are typically more stable in temperature.
Is the lifetime model proposed by EPC evaluated by any third party?
Yeah. So, like for example, so this is let me show you. So this is a paper that we published recently in IEEE power, transactional power electronic devices. It's been peer reviewed, and here's the test result. The answer is yes.
The 5 main stressors you listed, which one is the most important?
I think probably based on the study, I think temperature cycling, especially temperature cycling that better emulate the motor drive, is a very rapid switching, very rapid temperature cycling. That's something I think we are still in the process of developing a better model for motor drive. I think that's something we need to spend more time and effort. We are doing that, rapid temperature cycling.
How do GaN devices perform under varying load conditions in motor drives?
Load condition. So Andrea, can you help that with that question?
I mean, it's kind of a generic question. I think you know, as always in most applications, there with power semiconductors, there's really 2 big or maybe 3 big limits. One is the voltage. So I think in terms of voltage, there is our devices, for example, usually have a 20% over voltage rating, while silicon has an avalanche rating. So there's some difference in behavior there that you have to consider if that's a limitation that is important for you, for example, in braking. There's absolute current, maximum current limitation. I think there, it's should not, it's listed on the data sheet. I don't think you can, it's a similar, let's say, similar topic as silicon and GaN. So there's a maximum current you can carry. And finally, there's temperature, which is usually the most common limitation. Again, same topic here. You have to, as I mentioned in a previous answer, the thermal analysis of your system is very important to ensure that in all conditions you're staying within the temperature limits of the devices. And I think there, the fact that our devices have the ability to topside cool them in terms of surface mount device gives a lot of advantage versus a standard silicon package where you will have a harder time to cool the device. So that might give you some advantages in some operating conditions.
Have you tested DVDT immunity in extreme conditions? And what's the max DVDT GaN FET can sustain or achieve?
I think the answer is yes, we have. We actually did a lot of this kind of high DVDT in LiDAR application, right, Andrea? So,
LiDAR is a little bit different. It's a
different,
but resonant topology, so it's not hard switching. I think there's no inherent limit in the DVDT, right? There's no latch up mechanisms in GaN. One of the concerns people have with high DVDT is typical Miller shoot through, right? And in terms of Miller shoot through, we do design our devices to have the Miller ratio, which is the ratio of the capacitances, to be below 1, which guarantees basically in most operating conditions that you will not have self turn on during high DVDT events. I think that's the main concern typically people have.
Okay. Our customers typically require very slow switching speeds to reduce EMC emissions. Would GaN FETs still provide a benefit at slow switching speeds? And would this slow switching speed impact reliability?
Andrea, what do you think?
So I think slow switching speed is the main trade-off will be increased switching losses. So that's a trade-off the designers can make depending on what their, what basically their DVDT limits can be. So that's a loss trade-off. In terms of reliability, I don't think so, right? I mean, the fact that you spend more or less time during transitions probably does not have a major effect on reliability. Schenke, what do you think?
Agree. I think if you spend more time in transition, that means you have less ring, less over voltage or effect. So, yeah. And the thermal probably is more is easier to get to an equilibrium, so to speak. So I think probably it's a less harsh condition in terms of reliability.
Do you have any advice on controlling gate to drain capacitance for controlling voltage slew rate?
I don't recommend using capacitance to control the slew rate. It's first of all, it gets rid of some of the advantages of GaN, and then it's actually quite tricky to do. I think our devices, GaN devices in general, are very linear and very easy to control with a gate resistor. So that would be the preferred method to control the VDT.
If the load is changing, would this affect the output ripple or the smoothness of the ripple waveform?
What do you think? Yeah, I mean,
I don't know. I think this is a motor drive specific question. I mean, there is some variation of DVDT and DIDT with current because of the gate drive circuit, right? So the Miller plateau and those things change with output current, and so there will be some slight changes in those DVT and DIDT which might affect those ringing, I guess.
What thermal management strategies are necessary for GaN devices?
Well, you got to cool them like any power MOSFET. For a surface mount device, the advantage of our concept packages and both the chip scale and the QFNs is that you have two paths of cooling. You have basically the standard for the PCB, and that we have basically you do that by two things: by adding a lot of copper next to the device on the first layer, and by adding vias to bring it down to the other layers. That's very common for any surface mount device. But the other advantage is the topside cooling, and that's really should be the main path in most high power density designs, because you have direct access to the top of the devices, and so you can put a small thermal interface material and a heatsink and get extremely low junction to ambient to junction thermal resistance that will which allow you to cool the devices very effectively. When you do this top-sided cooling, the quality of the TIM is very important. So very high thermal conductivity TIM is highly recommended.
Okay. Can GaN FETs achieve full operation at higher temperatures up to about 300 degrees C without affecting the switching capabilities?
Our devices are rated at 150 degrees.
Yeah, so well, that all depends on how long, the duration. So if you are talking about 10 minutes, no. If you talk about 1 microsecond, the answer is maybe, but that's something we need to look into more. So you just look at our phase reliability report. I think 14, we specifically test. So we did some extreme junction temperature testing. Yeah, so you can take a look.
What are the challenges and potential solutions in developing accelerated stress testing protocols that can adequately capture wear-out mechanisms in GaN devices, considering the need to extrapolate accelerated test data to real-world operating conditions?
Well, I think that's why we are having this seminar. But so we're trying to publish as much information as possible to document the information and learning we have developed over the years. Probably just if you want a specific answer, just let us know. We can talk offline. Yeah.
What are the dynamic mechanical stresses experienced by motor drive components such as bearings, shafts, and couplings under varying load conditions? And how can advanced structural analysis techniques be used to optimize the mechanical design for extended lifespan and reduced wear?
I think we are the wrong people to answer that question.
That, yeah.
Well, just from the GaN transistor point of view, so bending is we show the bending test, but on the vibration side, so there's a specific standard for test specs for vibration, but typically my conversation with the expert is that our GaN FET is very small. Mm-hmm. So you don't get is very low risk on the vibration. I think bending is actually one of the more stringent tests based on our analysis. That's why we did experiment where result shows there's no issue at 2 millimeter max bending. So just for information, actually we took everything 10 devices to 10 millimeter. So we still did not see any significant horizontal shift.
Okay. In the context of regenerative braking and energy recovery systems in motor drives, what are the complex challenges associated with managing the rapid changes in power flow direction and magnitude? And how can bidirectional power converters be designed to handle those stressors effectively?
I don't think this is a GaN specific question. This has to do with how you control your bus voltage based on braking, for example. And typically motor drives during braking, if you have significant operation conditions in that context, you will use some way to either regenerate the energy back to where your power source is or dissipate that energy into a resistor. Those are the two typical methods used. I don't see any difference when you use GaN.
Yeah, use GaN, just one comment that as just the current flow different directions, but I think what the reverse conduction when the current go from source to drain. So there's nothing really different compared to current going drain to source. The only challenge is that's why I think in the motor drive we are developing, we are always switching, so it doesn't really make much difference.
Okay. The GaN FET shows a positive temperature coefficient as compared with MOSFETs, so it can operate in parallel to increase current capacity. Do you have any sort of recommendation on the maximum number of EPC FET devices that can be operated in parallel?
I think that's a specific design. We have customers that use a whole bunch of them. I can tell you that.
Yeah.
But you're right. I think the RDS-on is positive temperature coefficient similar to a silicon, so that's very good. It also has a very stable threshold voltage and temperature, so that also helps for dynamic sharing, which is also something you should think about. So we have actually several boards and app notes detailing how to also not only improve the steady state current sharing, but also the dynamic current sharing, which is actually quite significant. That can be a real limit when you want to parallel many devices in parallel. So the dynamic sharing becomes very important. And again, we have several recommendations, including some motor drive boards. I don't know if they're out yet, but they will come out very soon with the parallel devices specific for motor drive. So take a look at our website for that information.
Okay. The GaN reverse conduction with VGS at 0 shows a higher VSD typical than MOSFETs at 1.7 volts to up to 2 volts. What is the reason for that?
Okay, so that's just because we have asymmetrical lateral divide. That's something I want to emphasize on the previous question too. GaN is a lateral device. All source, let me show, probably is better. This is a better image. Here. Okay. So it's a lateral device. So I think this is a better demonstration of the question to answer that question. So source right here, gate right here, drain right here. So the current conduct laterally through the electron, two-dimensional electron gas beneath the GaN from barrier, because the asymmetry of the power devices, that's why the VSD rating is higher than the threshold voltage rating, which is you control the gate to source. So in this case, you are basically the VGD. So that's explain the difference.
Okay.
Just to add a comment for if people are used to a silicon MOSFET, in a silicon MOSFET, there's a diode. And so the conduction mechanism here is different, as
right.
Shanker were explaining. So
yeah, so when you're that's why
diode.
Yeah, that's why explaining when you switching, you turn on the device, doesn't matter the current go from here to here or here to here. It's essentially the same thing compared to which is different from silicon.
On slide 33, how many different samples were tested for short circuit? And are the results presented this slide repetitive?
So in here, only here we tested 8 devices. Here we just randomly picked one. We did one, but yeah, that's what we did.
Okay. Do you do short circuit testing as a part of production testing?
No. But we will do more in the very near future, to cover different die size, different dimension, different RDS-on, different package too. So that's something we're working on.
Okay. Well, thank you, Shanke. Thank you, Andrea. Thank you, everyone, for attending. If we did not have a chance to answer your question, we'll reach out to you with a response. Likewise, if you have any additional questions afterwards, please send them into info@epc-co.com. You should receive a follow-up email within 24 to 48 hours with a link to view a recording of today's webinar. And lastly, a webinar on GaN basics and applications is scheduled for the 6th of September at 10 a.m. Central European Time. Additional webinars will be held in late September through October in various regions and time zones. So please check the website epc-co.com for more information and to register. Thank you for joining us today and have a great rest of your day. Thanks, guys.
Thank you.